Team Singapore, and today I'll be reporting on problem number 8, Euler's pendulum. The problem statement tells us to suspend a magnetic rod underneath a neodymium magnet and to deflect it. We have to study the motion of the rod under various conditions. The relevant parameters here are the length of the rod, the plate thickness, and initial angular velocity. Here's my concept outline for today. I will first begin with a preliminary account of the phenomenon, and then qualitatively discuss the phenomenon. Then, we will theoretically model the motion of the rod and end off with an experimental investigation. So let's start with the preliminary account. Here's my experimental setup. We placed a magnet on top of an acrylic sheet and suspended a rod made from magnets underneath. To determine the orientation and position of the rod, we color the bottom of the rod green and carry out image binarization, fitting an ellipse to the image. We observe that with minimal initial angular velocity, the pendulum appears to undergo a back and forth rocking-like motion. However, when provided an initial angular velocity, it rotates, showing that initial angular velocity is significant toward the pendulum's motion. Analyzing the motion within a short period of time, we see that the rod's contact angle theta, shown on the top right corner of the screen, undergoes oscillation. However, over a longer period of time, we see that the contact angle decreases, with oscillations becoming smaller. To determine whether the rod is sticking or slipping, we place a red marking on the rod and track it. Plotting the x, y, and z position of the red marking, we see that when it is in contact with the plate, denoted by the green regions, the velocity is 0, implying the contact point is sticking. Now, we shall move on to a qualitative account of the phenomenon. We note that in an ideal scenario with 0 initial angular velocity, the rod will swing back and forth, colliding with the plate. However, if the rod is provided with an initial angular velocity, it is able to undergo rotational motion. To describe the subsequent motion of the rod, let's consider a rod with a high angular velocity. There will be a large torque due to the centrifugal force, meaning the centrifugal torque can overcome the magnetic torque, resulting in a net counterclockwise torque. Hence, the rod will swing upwards, and the contact angle, which is once again shown on the top right corner, increases. As the rod swings upwards, the magnetic torque will increase, and the pendulum will eventually reach a maximum contact angle. Now, there will be a net clockwise torque, causing the pendulum to swing downwards and the contact angle to decrease. Similarly, for a low initial angular velocity, the pendulum will swing downward to begin with. Finally, we shall discuss the effect of damping. As discussed earlier, the rod will have a changing contact angle over time. To describe the subsequent motion of the rod, let's analyze the first half cycle of the pendulum. As the rod swings downwards, drag opposes the motion of the rod and acts upwards. Similarly, drag opposes the motion of the rod in the second half cycle. Since drag always opposes the motion of the rod, the amplitude of contact angle oscillations will decrease over time. In addition, as the rod rotates, energy is dissipated through drag and rolling friction, resulting in the rod's velocity decreasing. By analyzing the rod in the side view of the rotating frame, we can see that the centrifugal force it experiences will decrease over time. This means that the anti-clockwise torque has decreased and the rod will swing downwards, eventually coming to rest. With that, let us now discuss our quantitative model of the phenomenon. To model our magnets, we need to model the magnetic field due to a small wire element by using the Savart law. Using this, we determine the magnetic field at any point in space by modeling it as a current cylinder and integrating over its surface. Note that in these equations, A is the surface current magnitude, representing the strength of the magnets. To model the magnetic force acting on the rod, we can also treat it as a current cylinder and use the Savart law to once again obtain the following equation, allowing us to determine the horizontal and vertical magnetic forces. Hence, we can now model the motion of the rod. To do so, let us start by analyzing the relevant degrees of freedom, two of which describe the contact point. One is the distance between the center of the top magnet and the contact point, denoted by R contact. And the second is the angle the contact point makes to the horizontal, which we denote as alpha. For the orientation of the rod, the 3 degrees of freedom correspond to the Euler angles, namely psi, phi, and theta, which we illustrate below. Hence, we can then express the angular velocity and rate of change of angular momentum, which equates to the net torque in terms of the Euler angles. Writing down Newton's second law, note that contact force consists of weight, normal contact force, magnetic force, drag, and friction. Taking the talk about the center of mass, we are able to obtain the following equation describing the rate of change of the rod's angular momentum. We then solve these equations along with the no-slip condition for the 5 degrees of freedom of our system. Now, we shall move on to our experimental verification. Here is my experimental overview. We will start with a characterization and then discuss the trajectory of the pendulum itself. Lastly, we shall discuss the effect of relevant parameters. To characterize the strength of our magnet, use a Hall probe and measure the magnetic field along the axial direction. We then fit it to a curve to obtain the surface current magnitude. To characterize the coefficient of rolling friction, we roll a magnet down the ramp and check its position. Using Newton's second law and the torque equation, we fit the position to obtain the coefficient of rolling friction. To characterize the drag coefficient of the rod, we check the amplitude decay of pendulum oscillations. We then solve the equation of motion, where k is the drag coefficient, and fit the trajectory to obtain k. Hence, we can now predict the motion of the rod, and we see a good agreement between theory and experiment from the side view. And we once again see a good agreement from the bottom view. Next, we will discuss the trajectory of the pendulum. As the variation in the contact point radius is very small, we shall not be discussing it due to time constraints, but welcome any discussion during the opposition. Let us first investigate how the contact angle changes with time. We see that generally, the contact angle decreases over time due to damping. Similarly, the amplitude of contact angle oscillations will also decrease over time due to the effects of damping. Zooming into the graph of contact angle against time, we compare this to the graph of angular velocity against time. We can see that as contact angle decreases, the angular velocity increases. Likewise, as contact angle increases, the angular velocity decreases. Now, we will discuss the effect of relevant parameters on our system. Note that we shall only discuss the effect of these parameters on contact angle, as we have previously illustrated the relationship between contact angle and angular velocity. For all the graphs shown in the next section, we have plotted both theory and experimental data over 10 seconds. However, for visualization purposes, we shall only show the first 0.8 seconds of motion. We first vary the plate thickness while keeping other properties constant. We see that the amplitude of oscillations increases as thickness decreases. To explain this, we realize that the only effect a thinner plate has is that the restoring magnetic torque increases. And with a larger restoring torque, the pendulum will swing further downwards. We may also compare the periods of oscillation, and we see that a thinner plate results in a smaller period of oscillation, as a higher restoring torque causes the pendulum to more quickly swing towards equilibrium. Now, we vary the number of magnets in the rod. Surprisingly, we see that the amplitude of oscillations actually increases with less magnets, although the magnetic torque decreases, which is contrary to what we previously established. This is because changing the number of magnets not only affects the magnetic torque, but also affects the moment of inertia and mass of the rod. Comparing between a rod with different numbers of magnets, we see that a rod with less magnets will firstly have a lower moment of inertia about the axis shown in red. The rod will also have a lower magnetic torque and the lower mass. Out of these effects, we note that the change in moment of inertia is the most significant. Hence, returning to our earlier graphs, as the shorter rod has a lower moment of inertia, it will have a higher angular acceleration and swing downwards more, resulting in a higher amplitude of oscillation. Additionally, a shorter rod has a shorter period for the same reason. To investigate the effect of initial angular velocity, we first define the amplitude of contact angle oscillations, theta A, where a positive value indicates the rod has swung downwards, and the negative value indicates the rod has swung upwards. We plot that against the initial angular velocity. We observe that for smaller angular velocities, the pendulum swings downwards to begin with, but with higher angular velocities, the pendulum swings upwards. This is because a larger angular velocity results in a larger centrifugal torque, causing the pendulum to swing upwards more. Furthermore, we also observe that at a low initial angular velocity, the circular flat face of the pendulum comes close to but does not hit the plate. We can verify this by zooming into the graph of contact angle against time for the low initial angular velocity case. And we see that the rod indeed comes close to but does not hit the plate and will quickly swing back upwards instead. To explain this, let's consider the initial release of the pendulum at a higher contact angle theta. In this case, case, the magnetic torque is much higher than the centrifugal torque due to the small initial angular velocity, causing the pendulum to swing downwards a lot. At lower contact angle, since the rod has been given a non-zero vertical component of angular momentum, to maintain the no-slip condition, the rod will have a very high angular velocity. This causes the centrifugal torque to be higher than the magnetic torque, ultimately causing the pendulum to swing upwards again. In summary, no collision occurs even with a low initial angular velocity. Hence, we can now see that the back and forth motion that we observed earlier is not due to collisions between the entire bottom face of the rod and the plate. When the rod is released, it will firstly swing downwards. Once it is at lower contact angle, it will undergo a fast rotation of 180 degrees, after which it swings back up from the opposite direction due to the centrifugal torque. We define another property of the graph, which is the period of the first oscillation, and plot this against the initial angular velocity and observe an increasing trend. To explain this, let's consider the magnetic torque acting on the rod. Note that this torque causes the rod to swing downwards. You can see that the torque increases at a decreasing rate. Returning to the graph of period, you can see that this means that a rod with a higher angular velocity will have more gradual changes to the magnetic torque, resulting in a lower return torque, hence a larger period. To summarize my report, I have firstly qualitatively discussed the importance of the initial velocity or trajectory, the causes of contact angle oscillations, along with damping. Quantitatively obtained the equation of motion of the rod while modeling damping and considering rolling friction and drag, and experimentally investigated numerous relevant parameters like plate thickness, number of magnets, and initial angular velocity on the amplitude of oscillations and the period of oscillations. I have also characterized numerous relevant parameters to obtain these fits. Here are my references. Thank you.
So 2 minutes for questions by the opponent.
Okay, anyone here? First question.
You can't quite hear what you're saying.
First question. Do you have a chart of a combination of theta angle over time under different angular velocities?
Sorry, theta against time.
Yes.
No, we do not. We only have the oscillation amplitude.
Okay. Have you measured the static friction and kinetic friction coefficient between the plate and the pendulum?
Yes, we have. And actually, we have accounted for the slip-tick transition in our theoretical model. And we noticed that the pendulum does not slip for a very long period of time.
Okay, thank you. Next, the following questions are about the linear motion. Is the contact point always on the top edge of the pendulum, the circumference?
Yes.
For colliding, how do you quantify the energy dissipated, or you just ignore that?
As mentioned in the report, the rod actually does not collide with the plate, or
Okay,
instead
thank you,
it swings back upwards.
Next, the following questions are about the 3D motions. How does the normal force between the plate and pendulum change over time? Constant, increase, or decrease?
If theta is lower, the normal force will increase.
Thank you. What provides centripetal force for the pendulum?
The magnetic force and potentially static friction.
Okay, thank you. Have you analyzed the rotation of the pendulum itself, the angle of psi you defined?
Sorry, psi dot or phi dot?
Psi dot.
We have not investigated psi dot, but
Okay,
we believe that psi dot will be related to phi dot with the no-slip condition.
How do you consider the kinetic friction in your model? Like you could.
We have accounted for the slip-tick transition as I mentioned earlier, but we actually note that the pendulum does not slip for a very long period of time. Like generally, it's the first 0.1 seconds at maximum.
How do you prove that your motion is pure rolling instead of slight slipping between the plate and pendulum?
You mean how do I prove the motion is rolling without slipping?
Yes, since you only consider rolling friction as I think.
We have checked the contact point and we know that the contact point is sticking when it is in contact with the plate.
Even if higher angular velocity, this proof is still objectable.
Sorry, I don't quite get what you mean.
Okay, next
So your
question.
times offered 5 minutes preparation time for the opposing team.
答案我传你那边有公式，等会儿把答案放到你那边。
好。
就每一题要对应他那边的题。那种。
好。
然后你这边要做很这样那个，我讲一个，然后
verify function of the motion。对，然后你这边要讲说，我们把它整个都 angular velocity 把这个生成，然后你要不要讲那个 miss 的 conical motion？miss conical motion。然后 magnetic stress 那个，对吧？是 magnetic stress。好 conical motion。conical motion。这里。好的。important。然后这个 deviation 是，你看到它前面有一张图是theory 跟理论比，但是它不是它的比例这样，这样怎么像？就是它的 theory 就这样，那就可以从这里连接到一个 console， 就是有些比较高，有些比较低。好，对吧？这他们是蛮准的。然后我直接把边放在这边，然后你就把现象分散。
它是解分散。
然后你可以说 no explanation of possible deviation。虽然说，然后还有他们没有那个了，没有 period。没有，他有就不是 period。有他这个有时候那个 decrease。那他有讲为什么？
有。
他有讲好，要看一下。
最后一页。
好，我没有听错。
这个。
然后他讲的
最后一页。
你要讲 collision， 你还有要讲 collision。
他前面有。
还是还有3个。还有3个，你有要讲 collision？讲一点，我直接跟他 suppose idea。他问你说可不可以 increase the volume of the microphone？ 你这样继续跟你讲，不要这样玩。如果
我就是你那只手。
没有，你是对着这个，你是这样会爆音。没关系。你就清楚了。不要。这样子。
刚超小声诶。
不要，不然你这样。
刚是真的超小声。
好吧，这样子。
好，你这样。
对着你就好了。抱没关系啊，他抱了就好。
因为开了麦克风出来，应该还没。
degrees of freedom. We will try to improve it.
你要回复我说。
我问他们有没有用那个什么，看他们谁要来，谁不用来。Pardon, before the presentation started, I want to ask Team Singapore who will be writing the whiteboard because I need to use the whiteboard later and I need to give you the permission to write on the whiteboard.
Your microphone is still very noisy, but the whiteboard you are now, you have the presentation rights, and to use the whiteboard you can skip the Benji?
No.
Yeah, so if you have the presentation rights on the right hand side of the screen, there should be a series of buttons which you can use to draw on the whiteboard, and then if you wish to allow the reporter to also draw in the lower right corner, I believe there's a button to enable the multi-user whiteboard.
Okay, I found it. Thank you. 那你就大声点好，好，我就大声。对。
screen, share your screen. And it's over.
It's over here. 大声，对着讲大声。Okay, can anyone see
You see the
the
screen.
presentation? Okay, I'm going to start. Honorable juries and fellow competitor, I'm the opponent from Team Taiwan, opposing problem number 8, Euler Pendulum. The problem say that take a stick plate of non-magnetic material and fix a neodymium magnet on top of it. Suspend a magnetic rod, which can be assembled from cylindrical neodymium magnets underneath it. Deflect the rod so that it touches the plate only with highest edge, and release it. Study the motion of such a pendulum under various conditions. For the overview of the report, first, the phenomenon explanation. The reporter divided into two phases, include the minimal angular velocity and the state with angular velocity. And we found that collision happened when no angular velocity was given. However, the reporter ignored that since the initial conditions is not well controlled in his report. And we believe that the 3D motion, we can divide it into a circular motion and elliptical motion. The elliptical one is giving it arbitrary angular velocity. And from the chart of the reporter show, there is a boundary between the theta angle decrease and increase. That is how we define circular motion. The theta angle will constantly decrease. And for the dissipation part, the reporter did some explanation about the friction, air drag, and eddy current that also acting on the pendulum. And for modeling part, they define 3 degrees of freedom, including theta, phi, and psi. However, the reporter missed analyzing the angle of psi in the experiment. He considered one contact point and model the magnetic field. For the improvements part, we believe that they can prove whether the pendulum is pure rolling or not by analyzing the angular velocity of phi and psi and find the velocity difference. This can prove that whether the motion is pure rolling or not. For experiments parts, we believe that we can divide it into linear mode, circular mode, and elliptical mode. The linear mode is with low angular velocity. However, in the reporter's report, no collision was found because the deviation of initial conditions. And circular mode, we believe that there is a boundary that I mentioned that's giving it specific angular velocity. The theta angle will not significantly increase or decrease in the initial part of the phenomenon. This is how we want to discuss the nth part. And for the damping part, we didn't find a measurement of kinetic friction coefficient in the modeling, so I will discuss the dissipation later. These are the discussing points. For the 2D mode, although the reporter didn't conduct any experiments, if the initial condition is ideal, this should happen in the phenomenon. And we'll try to analyze the forces acting on the pendulum, some quantification of inelastic collision, and try to draw the energy of the pendulum over time. And this can show many information that I show on the PPT. For the 3D mode, we believe that kinetic friction that the reporter doesn't prove that exists is one of the major dissipation in the model. So we'll try to explain the kinetic friction depending on the normal force. For the centripetal force, the reporter didn't clearly mention. He only mentioned the centrifugal force acting on the system and didn't mention why the conical pendulum exists. That is theta angle over time. I mentioned the short question that we should have a comparison of the conditions. Next is the discussion part.
Could I have screen sharing permissions?
I think I will use the whiteboard to discuss with you first. Is that okay?
But if I share my slide, then I can give you whiteboarding permissions also.
I think that is not. I'll use the black whiteboard in the meeting first.
Sure.
Okay, first I would like to focus my discussion on the 2D part. Since you didn't have an analysis on this part, can you please preliminary analysis the forces and draw it on the whiteboard? What are these forces acting on this pendulum?
Sorry, how do I draw on the whiteboard? Do I have permissions?
I think you have now allowed the permission.
Okay, well, let's bring this sorted out. There's a weight acting downwards on the pendulum at the center of mass.
Okay, weights acting downward at the center of mass. I'll draw
And
it
there's
for you.
yes.
And
And there's a magnetic force acting somewhere towards the top right corner.
everything got somewhere to the upper corner. We define it as a magnetic force. And other forces,
There's static friction at the contact point.
static friction at the contact point. So let me separate the magnetic force into the horizontal component and the vertical component. Have you measured that by multiplying the normal force times the static friction coefficient, is that bigger or smaller than the horizontal part of the magnetic force? Have you compared that?
Sorry, I'd like to add that there's also the normal contact force acting at the contact point.
Oh yes, I forgot it. Sorry. Yes, there is a normal force. So,
Could you let me share my screen? I have an explanation for this in my slides.
can you just simply verbally explain? Did you analyze that whether the horizontal part is bigger than the normal force times static friction coefficient?
We experimentally characterize the static friction coefficient, and when we input it into our simulation, we at every time step we check whether the static friction exceeds the mu/s(n) term, and if it does, that will mean that the rod is sticking. But in our simulation, for a majority of the motion, it does not stick, and the static friction does not exceed mu/s(n).
So I think in this part you should consider that when the static friction times normal force is bigger, is smaller than the horizontal part, slipping will happen. So the contact point will be moving. Okay, thank you. Next, I want to discuss the dissipation. Have you tried to found the collision part, or it always doesn't exist in your experiment? Because if ideal initial condition controlled, this may happen. So collision should be observed in the experiment.
If there is zero initial angular velocity, then I agree that there will be collision between the rod and the plate. But even with a small initial angular, like a very very small initial angular velocity, I believe there will be no collisions, and I did not observe it experimentally.
So I believe this part, some initial condition could be controlled, because if we divide the pendulum motion into 2D and 3D part, we miss half of the motion of the pendulum, and we believe that the collision part is the important, that's the motion of the pendulum that the problem statement required.
Sorry, how would you suggest that I release the pendulum with absolutely zero initial angular velocity? Just for example, by using a string, there will also still be a very small amount of initial angular velocity.
Maybe an electromagnet on top of the pendulum, and you cut off the currents, then you could avoid the deviation from your hand.
But that will affect the motion of the pendulum since it's magnetic.
I believe this is not the main discussion part, but the 2D motion part, ideally, it should exist in this phenomenon. Okay. Since we just discussed the energy dissipated, can you try to draw the chart of total energy of the pendulum over time on this chart?
I do not have screen. I don't think I can draw on the whiteboard.
No, perhaps.
Oh, okay, yeah, I can. So we can see that the pendulum will start. Sorry, you're talking about the total energy, right? Including gravitational potential, magnetic potential, and kinetic energy, right?
Yes, all kind of energy they do. Adding them all together.
We will expect that the total energy goes down, and I believe it will look something like. It will look something like this.
For this part, since you mentioned that if ideal condition controlled, collision will happen, and we believe that the bigger energy will be dissipating in this part. So there should actually be a gap of the energy. Do you agree this part?
If there were to be collisions in the system, I believe that the energy will it will have gaps which I agree with. But in our report, we do not believe that there are any collisions observed. Hence, we do not believe there will be any gaps that we see.
Can you rephrase again?
I agree that if there were collisions, what you described would be true. But in our report and our experimental investigation, we did not observe any collisions, and we believe that it is very difficult to observe collisions.
Okay, I understand your point, but if this charge was drawn, we can also see that the period change of the pendulum is gradually smaller. Since you mentioned that in your experiments the period time will decrease, right, when the magnetic get closer.
Sorry, I couldn't quite catch that. Are you asking that as the motion progresses, will the period decrease?
Yes.
Yes, I actually investigated the effect of the initial release angle. It's in my hidden slides, and we note that as the initial release angle increases, we will observe an increase in period. And since as the motion progresses, we will expect that the contact angle decreases, resulting in a smaller period. And this makes sense intuitively, since the pendulum has to swing across a shorter distance.
Okay, I understand that the restoring force when the magnet get close will be stronger, so it results in decreased period. And thus, can you try to draw a theta angle of no initial angular velocity over time?
Sorry, this is of the no initial angular velocity case.
Yes. Can you draw the theta angle over time?
Sure, it will look something like this. Sorry, I need to. You observe that the peaks noticeably drop after each time, and I'm sorry that my drawing is quite bad, but the bottom peak would actually lie at theta equal to 0.
Okay, I understand for this part. Let's go to the cone part. Can you explain how do the normal force change during the motion? The normal force acting down the system. There is a normal force.
As the contact angle decreases, the normal force will increase.
So the angle decreases, the normal force will increases, right?
Yes.
For this part, I believe I can quantify it for you, since there is a gravity acting down and vertical components of magnetic force are acting up. So the normal force should actually be like this: the vertical component minus mg minus mz double dot in this direction. So I think you can draw the normal force over time in your experiments. Do you agree with that?
I believe that will be possible. Yes.
Oh yes, and for the next part, if you can calculate the kinetic friction exists, or you mean your rolling friction coefficients, you times your normal force, you can calculate the energy dissipated. Do you agree with that?
Yes, we have accounted for both rolling friction and air resistance in our report.
So I think you can analyze how will the energy dissipation rate change over time in your experiments. Okay, next part I want to investigate.
Sorry, to clarify, you are mentioning that if I demonstrate, if I calculate the rolling friction and the air resistance, then I can calculate the energy dissipation rate that way.
Yes, this is the consideration of all kinds of dissipation. Next is how will the centripetal force acting on the system, since there is a conical oscillation.
Sorry, I couldn't quite catch that. Could you please repeat what you were saying?
How does centripetal force act on the pendulum?
I believe that there are two possible sources of the centripetal force, one of which would definitely be the magnetic force, and another possible source would be static friction depending on the direction that it is acting in.
Oh, I understand, like this horizontal part. So I believe that since you can calculate normal force as well, you can find out when the centrifugal force is equals to the centripetal force, you can find the conical motion. And if
when it is circular motion.
Yes, and if you change the equation, it can be written like this, and you can get the omega of phi over time. Yes.
I think the discussion is over. Thank you very much for the discussion.
Okay, thank you.
So summary by the opponent for a minute.
I think Vincent Chang should get the permission. Okay, here's the discussion summary from the opponent. For the 2D part, we believe that the horizontal cause the pendulum horizontal component cause the pendulum to oscillate. And if we draw the chart of energy over time, we can find that the period will decrease because restoring force increases. Also, the gap of the energy will show that the dissipation of collision. For 3D part, we believe that normal force can be calculated from the equations that shown. We can get the normal force and friction coefficient and get the energy dissipated over time. And the centripetal force that I just mentioned can be it is the composition of the horizontal part of magnetic force and also the static friction. And if it is balanced to the centrifugal force by changing the equation, we can find out that the omega of phi will equals to a square root of horizontal component of magnetic force over m times the radius. So this can get the data over time. Thank you.
Thank you, and concluding remarks by the reporter.
Could I please have screen sharing conditions for the confusion? Sorry, give me a minute to connect my slides. Okay, thank you. So to summarize the discussion, we firstly discussed about the 2D case, and we have discussed the possibility of slipping. And I believe that for the majority of the motion, the pendulum will actually be sticking. But depending on the initial conditions, it is possible for it to slip at the very start of the motion, which we have accounted for. Next, we discussed the case where the collision in the case of the zero initial angular velocity, and I believe that the energy would show a step-like function, but it was not observed experimentally. Next, we also decreased how the period decreases over time, and I agree with this because the contact angle decreases over time, resulting in a decrease in period. We then discussed about the normal force, and we agree that the normal force increases over time as theta decreases. Lastly, we discussed about the circular motion, and whether the reporter believes that it is possible, whether the opponent believes that it is possible for circular motion to be observed with the centripetal force counteracts the gravity. I believe that we also need to consider the magnetic force and static friction. So to conclude my report, I provided a qualitative overview of the phenomenon, quantitatively modeled the phenomenon accounting for 5 degrees of freedom, and experimentally investigated numerous relevant parameters. Thank you.
Thank you. So the jury questions. Who wants to start? Stefan.
Okay. Thanks, reporter, for the great report. But I'm just curious. You showed a great experimental plot of the oscillations, and it's clearly seen that these oscillations are not harmonic, so it doesn't perfectly mimic the harmonic function. So, did you try to study how is it far from the harmonic oscillations? I mean, how does the form differ from the sine or cosine?
Sorry, to clarify, are you referring to this graph?
I'm referring to the further plots of the yes, the contact angle time and this length. Yes. So here we can clearly see that like the phi dot is not harmonic.
I believe that the force, it wouldn't be harmonic since the force isn't linear, and there are non-linear components from both the gravity and the magnetic force. And we haven't quite investigated this yet, but I believe that a possible way to do it would be to first consider the canonical pendulum, then from small deviations in angle, it will be approximately sinusoidal since we can perform a Taylor expansion of the motion.
Okay, thanks.
So next questions, Martin.
Yes, I have also a question to the reporter, please. There was in the discussion part some confusion about centrifugal and centripetal force. Could you briefly tell us if you used the concept of centrifugal force in your theory?
We only use the centrifugal force to qualitatively explain why the pendulum oscillates, but in our quantitative model, we did not work in the rotating frame, and we worked in a fixed coordinate system. So we did not need to use the centrifugal force in our equations.
Okay, thank you.
Okay, then I have a question myself. It's a very short question. Maybe I missed it, but how did you release the rod in your experience?
We released it by hand, but then we tracked the initial conditions of the rod, and we selected motions with similar initial conditions. So we released the rod many times before being able to obtain rods with similar initial conditions.
Okay, dann Hunko. We don't hear you, I think. Maybe type your question in the chat and then Stefan can ask this time this next question.
Okay, so I also have a quick question. Does the behavior of this pendulum depend on the initial conditions? So you provided like 5 degrees of freedom. So did you try to study how the oscillation depends on this? I mean, if you vary the angle, or if you vary the position of the pendulum and the suspended magnet.
We've investigated effects of changing the initial angular velocity, the initial release angle, and the initial contact point position. So for the initial angular velocity, if we increase the angular velocity, we will expect the pendulum to swing up higher initially. And for the initial contact angle, I have it in my hidden slides. We see that the pendulum actually swings downwards more if you release it from a higher angle, and the period also increases if you swing it from a higher angle. And lastly, for the contact point, I'm not sure if I have a video in the slides, but if you release it very far away, the contact point will first slip towards the center very quickly before exhibiting a similar motion to what we observed in our report.
Okay, great.
May I ask?
Okay, thank you.
Amy,
Yes.
yeah. I have
Yes,
a question.
we hear you. No.
Yeah, I have a question for the reporter. So, you mentioned about the Biot-Savart's law and air drag in the qualitative explanations. So, are they relevant to your experiment?
In the qualitative explanation,
Yeah, you mentioned both things.
the Biot-Savart law is actually used in our quantitative modeling of the phenomenon, and it is what we use to obtain a model for the magnetic forces and torques acting on the rod. And air drag is significant qualitatively as it is a possible cause of damping, which causes the rod to swing downwards more and also causes the contact angle oscillation to change over time. And we have also included this in our theoretical model.
Did you use the electric magnet?
No, we did not use an electromagnet. We used neodymium magnets. Because we use the current center model. Thank you.
Thank you. I think time is over for the questions, and now Martin, time is over, I would say. Yeah, we have to break 5 minutes.
记到，就是不差。